Whiplash is a serious public health issue around the world. Experts estimate that nearly 1 million people in the U.S. are injured each year in rear-end automobile collisions, with an annual cost of about $30 billion. Whiplash injuries are a modern phenomena. The term whiplash was first used in 1928, and whiplash injuries started to become more common after World War II with the rise in popularity of the automobile. Whiplash has been controversial since the 1950s, and remains so 50 years later. The greatest debate regarding whiplash today is the area of low-speed collisions, especially injuries arising from accidents with little or no visible vehicle damage. Most people are not aware that there have been literally hundreds of studies written on the problem of whiplash, and that since 1995, a number of respected scientists from around the world have made some exciting new discoveries that have uncovered how the human body can be injured in low-speed rear-end collisions. The goal of this video is to acquaint you with these discoveries, show you how low-speed rear-end collisions result in abnormal motion of the human spine, and describe some of the factors that can increase the risk of occupant injury in these collisions. This information can help us understand and treat whiplash pain, and can direct us to new ways to reduce the number of these injuries in the future. To understand the complexity of whiplash injuries, we first need to look at the basic physics of rear-end collisions. These simple concepts of physics explain how the vehicles and the occupants move during a crash. There are three concepts we need to understand: momentum, acceleration, and inertia. Momentum is simply the energy of a moving object and is mathematically described as being equal to the mass or weight of an object multiplied times its velocity or speed. From this equation we can see that the heavier an object is, or the faster it is moving, the more momentum it will have. For instance, a 2,000-pound car traveling 5 miles per hour will have only half the momentum of the same car traveling 10 miles per hour. Also, a car that weighs 2,000 pounds and traveling 10 miles per hour will have half the momentum of a 4,000-pound car traveling at 10 miles per hour. Momentum also has another important property. According to laws of physics, momentum in a collision is always conserved. That is, when two objects collide, the momentum that existed before the collision must be present after the collision. This is written as follows. As we see here, the momentum of Vehicle 1 and Vehicle 2 before the collision must equal the momentum of Vehicle 1 and Vehicle 2 after the collision. This is known as the law of conservation of momentum. Let us see how this relates to automobile crashes. First, we'll start with a car stopped at a red light. This is known as the target vehicle. It has a mass of 1,000 kilograms. But it has a velocity of 0 and therefore has a momentum of 0 as well. Now, the car behind this, known as the bullet vehicle, also has a mass of 1,000 kilograms, but is moving at 5 meters per second, or about 11 miles per hour. Therefore, before the collision, we have a momentum of 0 for the target vehicle, plus a momentum of 5,000 for the bullet vehicle, for a total momentum before the collision of 5,000. According to the law of conservation of momentum, the momentum after the collision must also be 5,000. But once the bullet vehicle strikes the target vehicle, the speeds of the two cars are different. After the collision, we find that the bullet vehicle has slowed from 5 meters per second to just 1 meter per second. Therefore, the momentum of the bullet vehicle is 1 times 1,000, or 1,000. Since the law of conservation of momentum requires that the momentum must be 5,000 after the collision, that means that the target vehicle must have a momentum of 4,000, and thus a velocity of 4 meters per second. That means that the target vehicle accelerated from 0 meters per second to 4 meters per second. Let's look at a different example, where the bullet vehicle has the same velocity as before, 5 meters per second, but weighs twice the target vehicle, or 2,000 kilograms. Instead of a momentum of 5,000, the bullet vehicle now has a momentum of 10,000. The target vehicle is again stopped and has a momentum of 0. So before the collision, we have a total momentum of 10,000. The bullet vehicle in this example slows down to 1 meter per second after the collision, resulting in a final bullet momentum of 2,000. To equal the momentum of 10,000 prior to the collision, the target vehicle must have a final momentum of 10,000 minus 2,000, or 8,000. Since the mass of the target vehicle is 1,000 pounds, the final velocity must be 8 meters per second. So, because the mass of the bullet vehicle was twice the target vehicle, even though the speed of the collision was the same as the first example, the velocity of the target vehicle has doubled from 4 meters per second to 8 meters per second. In other words, although the speed of the crash was the same, the collision was twice as severe because of the increased weight of the bullet vehicle. These two examples are simpler than what really happens during a collision, as we'll see later. But it does graphically illustrate that when we are looking at rear-end collisions, we need to not only examine the speed of the collision, but we also need to take into consideration the weight of the two vehicles involved in the crash. The second concept of physics is acceleration. It is described mathematically as delta V divided by delta T. Delta is simply the Greek symbol that means change in. So acceleration is the change in velocity of the object divided by the amount of time in which the acceleration takes place. In our earlier example describing momentum, we saw that in one instance the target vehicle accelerated from 0 meters per second to 4 meters per second. In practically every study on low-speed rear-end collisions, the amount of time that this acceleration takes place in is about 100 milliseconds, or 0.1 seconds. If we put these numbers into the equation for acceleration, we get a result of 40 meters per second squared. In the second example describing momentum, we saw that the target vehicle accelerated to 8 meters per second in the same amount of time. Thus, the acceleration in the second example is 80 meters per second squared. To simplify matters, engineers often use the term g-force as shorthand to describe acceleration. A g refers to the amount of acceleration that Earth's gravity exerts on objects. For instance, normal Earth gravity is 1g, and the complete absence of gravity is 0g, or zero gravity. Mathematically, 1g is equal to 9.8 meters per second squared. To calculate g-forces, we can simply divide the acceleration of the car, which was 40 meters per second squared in the first example, by 9.8, and we get a result of a little over 4 g's of acceleration. The final concept of physics that we need to understand when dealing with low-speed collisions is the idea of inertia. Newton's second law states that every body continues in its state of rest or uniform motion in a straight line insofar as it may be compelled to change that state by the action of some outside force. In plain English, this simply means that a stationary object will never move unless something else acts upon it to make it move. Likewise, an object that is moving will continue to move until something makes it stop moving. We can look at our earlier car crash model and see inertia at work. The target vehicle is stopped at a red light and will stay stopped until something makes it move. In this example, the bullet vehicle. Likewise, the bullet vehicle will keep moving forward until something makes it slow down. In this case, the car in front of it. And most importantly, inertia plays a critical role in how the human body moves during a crash, and is the primary reason why people get hurt in low-speed impacts. Let's now review the basics of a rear-end collision. The target vehicle is stopped at a red light. The bullet vehicle has both mass and velocity, and therefore it has momentum. The bullet vehicle strikes the target, applying an external force to the target vehicle. The target vehicle is accelerated forward rapidly. Now that we understand what happens to the cars during a rear-end collision, we can now examine the motion of the occupant inside the vehicle. First, we'll observe an animation of a rear-end collision as it appears without high-speed photography. Here it is again. Whiplash injuries take place very quickly, as you can see. The whole collision from beginning to end takes place in about 2/10 of a second, while all of the occupant motion takes only half of that time, about 1/10 of a second, or in a blink of an eye. Obviously, we'll need to slow this motion down if we are to understand what happens during a low-speed crash. We're able to do this as we have data from dozens of test collisions that have used human volunteers in low-speed crashes. These test collisions were carefully planned, and all of the occupant motions were collected via acceleration measuring devices and were photographed at speeds of 500 frames per second. This sophisticated technology allows us to observe the occupant motions during a crash in great detail. So now let's slow this collision down from 2/10 of a second to about 4 seconds. Let's now analyze this crash step by step. At the moment before the collision, our occupant is sitting upright in her seat, looking straight ahead. As the target vehicle is struck, it begins to move forward. Since the car seat is bolted to the target vehicle, it moves with the car. As we saw earlier, all objects with mass also have inertia, and the occupant's body is no exception. Since the occupant has inertia, her body is going to stay in the same position until acted upon by some outside force. In this case, the car seat back. Eventually, the car seat moves so far forward that the seat cushion is completely compressed, and the seat back begins to exert force on the occupant's lower back, and the occupant's lower back begins to move forward. Because the seat back is not perfectly vertical, the occupant's body ramps up the incline as shown here. The seat back is bending backwards at this point as it meets the resistance of the occupant. The occupant's upper back starts out farther from the car seat and moves forward later than the lower back. As the car seat reaches its greatest angle backwards, the upper torso is fully accelerated forwards with the car seat. The occupant's head, however, has no portion of the car to accelerate it forward, since this seat, like 80% of cars on the road today, does not have a proper head restraint. And since the head has inertia, it remains in the same position as it was before the impact. But the torso is moving forward rapidly. Eventually, as we can see here, the lower neck begins to pull the head forward, causing the head to rotate backwards quickly over the top of the car seat. At this point, there is a dramatic difference in how the torso and the neck are moving in relation to one another. As we can see in this graph from a crash test of 5 miles per hour, the torso accelerates much earlier than the head. In fact, the torso has mostly stopped accelerating by the time that the head reaches its peak acceleration here. Just at the moment where the head has reached its point of greatest extension, we see that the car seat begins to spring forward and move to a more upright position. Because the torso is now moving with the seat back, the spring action of the seat pulls rapidly on the lower neck, causing the head to rebound forward ahead of the torso. This results in very high peak head accelerations, as shown in this graph. As we can see, peak head accelerations increase dramatically at higher delta V's. A difference of just 1 mile per hour in delta V between 4 miles per hour and 5 miles per hour results in peak head accelerations that double. High-speed film footage was collected first in the 1950s, and scientists thought that these test collisions had found the answer to how people could be injured during a rear-end collision. The researchers saw the rapid backward motion of the spine, known as extension, and concluded that the injury was caused by hyperextension. That is, the spine extended too far back, causing injury to the joints of the spine. This hypothesis was supported by other researchers who found damage to the spine of cadavers that was consistent with this mechanism of injury. Other researchers, however, were skeptical of this theory, especially when it was applied to people who had been injured in low-speed collisions or accidents under 10 miles per hour. These skeptical researchers then measured the amount of extension that occupants experienced during test collisions and found that in low-speed crashes, the head did not extend beyond the normal range of motion of the spine. The engineers concluded that because hyperextension did not occur, injury was impossible in low-speed crashes. Another group of engineers and physicians, however, had become interested in a new line of study. These scientists realized that the occupant motion during a rear-end collision is much more complex than it seems. The complexity of a low-speed collision is evident in this chart. This data was taken from a test collision of 5 miles per hour. The first object to accelerate is the car itself, then the lower back, followed by the occupant's torso. The last thing to begin moving is the occupant's head, since the inertia of the head keeps it in place until it is moved by the torso and the car seat. Early on in Whiplash research, engineers focused almost exclusively on the x-acceleration of the occupant's head. X-acceleration is that which occurs in the front-back direction, or the horizontal plane. Later, other researchers noticed that there was a degree of z-acceleration, or in the vertical plane, when the occupant's body ramped up the car seat, but they assumed that this was unimportant. The human body is a vertical structure and is designed to absorb the force of gravity in daily life. Because of its design, it can handle moderate amounts of axial compression without difficulty. X-acceleration, however, is not handled as well by the body and results in what is known as shear forces. Even moderate shear forces can result in injury. Some scientists noticed upon examining occupant test data that the peak x-acceleration happened to occur at nearly the exact same moment as the peak z-acceleration. This is another graph from the same occupant test data we saw earlier. This was a crash test conducted at just 5 miles per hour. As we can see here, the peak axial acceleration or compressive force reaches about 15 Gs of acceleration, while the peak X acceleration or shear force reaches about 9 Gs at nearly the same moment. These scientists decided to investigate what effect this combined compression and shear had on the spine. But instead of simply observing the external motions of the occupant, they decided to measure what happened to the individual joints of the neck. To study this, a group of Japanese researchers subjected some test subjects to a low-speed whiplash impact, but photographed these tests using cineoradiography, a technique that makes an X-ray movie at very high speeds. This technology allowed the scientists to observe the motion of each vertebrae in the spine in slow motion. What they found was that rear-end collisions resulted in spinal motion that was far more complicated than the normal movement of the spine, and that this abnormal motion could account for the chronic pain seen in some low-speed whiplash patients. To understand how injury can occur in low-speed collisions, we first need to understand normal spinal motion. This is video fluoroscopy footage that shows the normal motion of the neck. As we see during normal flexion and extension, each vertebra contributes to the overall movement of the neck, resulting in a smooth, regular curving of the spine. This smooth motion of the spine is made possible by the facet joints on each individual vertebra. As you can see, the facet joints are angled backwards. During normal spinal movement, these facets glide across one another, allowing the spine a wide range of motion backwards and forwards. Up until 1996, researchers assumed that the spine moved the same way during a rear-end collision as it did in everyday activities. This simple whiplash motion was seen as normal position before the impact, extension backwards, rebound motion forwards, and then back to normal. The newer research, however, showed a completely different motion. First, the head and neck start in the normal position. As we saw earlier in our description of the occupant motion during a collision, the occupant's torso is moved forward first while the head stays in place because of inertia. This difference in the motion between the torso and the head results in a very rapid straightening of the cervical spine. As the torso continues to move forward, the head's inertia keeps it level and fixed in space. This results in a slight degree of flexion in the upper spine, with dramatic extension focused on just a few intervertebral joints in the lower spine. The researchers found that the spine formed an abnormal S-shaped curve at this point during the whiplash impact. Then, as the torso continues to move forward, the head finally extends backwards, resulting in normal extension of the spine. The head then begins to rebound forward. Now, let's compare the two motions of the spine. First, the normal extension. Now, the abnormal S-shaped curve. Ono and his colleagues then analyzed the data that they'd collected from their live occupant, low-speed test collisions. They found that the combination of compressive force and shear force altered the way that the vertebra moved in relation to one another. They first started with established knowledge of how the cervical vertebra move. Previous research had shown that each vertebra rotates around the one below, like this. This point of rotation is referred to in the biomechanical literature as the instantaneous axis of rotation, or IAR, and permits the smooth gliding motion of the facet joints. Ono et al. Then compared this normal rotation with the motion they observed during rear-end impacts and found that the point of rotation, or the IAR, actually moved during a crash. Instead of this motion, they found this motion. These findings prompted Ono and his colleagues to write, "This is a non-physiological motion of the vertebral segments." In summary, they saw that the spine was subjected to rapid compression, then shear, which caused abnormal motion in the facet joint, all from a collision of just 5 miles per hour. Shortly after this research was published, other research teams from the Yale School of Medicine and Wayne State University reported similar findings. A study conducted by Grauer et al. Was studying the problem of spinal motion at the same time. They examined the degree of rotation between each of the different vertebrae in the spine in a set of simulated car crashes in cadavers. They first measured the normal range of motion that each joint could handle, and then subjected the specimens to impacts of 2.5, 4.5, 6.5, and 8.5 Gs, similar to what an occupant would experience in a low-speed crash. Grauer found that the joints at C3, C4, C6, C7, and C7, T1 moved less than 5 degrees during normal extension. When the spine was subjected to greater impacts, the C6, C7, and C7, T1 joints experienced dramatically greater rotations than they could handle, while the C3, C4 joint stayed within its physiological range. Another team of researchers from Wayne State University was also studying the problem and performed some different experiments with cadaver spines. They found that the cervical spine does not handle the combination of compression and shear well at all. In fact, they found that the ligaments that hold the spine together weaken dramatically when compressed. As this graph shows, they found that the lower spine lost as much as 70% of its resistance to shear when it was compressed just 40 pounds. 40 pounds of force may seem extreme, but the study by Ono et al. Reported compression of 56 pounds in a collision of just 5 miles per hour. The final piece of the puzzle was discovered by another team of researchers who published their findings in 1999. These scientists decided to study in detail the motions of the facet joints during a rear-end collision. They carefully prepared a cadaver spine with special reflectors placed on each cervical facet joint. They then subjected the spine to an impact approximately equal to a collision of about 4.4 Gs, or what would be experienced during a low-speed crash, and recorded the motion with high-speed video. They found that the facet did indeed experience the abnormal motion that was seen by the other researchers. Instead of gliding smoothly across each other, as facets do in normal motion, the upper facet joint rotated abnormally and pinched the lower joint. Furthermore, these researchers found excessive flexion in the upper spine during the S-shaped portion of the whiplash motion. The authors of this study concluded, excessive stretching of the posterior upper cervical complex and the pinching mechanism due to compression and sliding of the facet joint may explain the presence of suboccipital headache and neck pain, respectively, in patients with whiplash-associated disorders. As we've seen in the last few years, a great deal of high-quality research has pointed to the cervical facet joints as a possible source of whiplash pain from low-speed collisions. One question remains. Do these engineering findings correlate with what physicians find in patients suffering from pain caused by rear-end collisions? The simple answer is yes. A great deal of research on the problem of whiplash has been conducted by a group of researchers at the University of Newcastle in Australia. As early as 1988, this group of scientists had begun to look at the facet joints as a source of chronic symptoms. Then in 1996, they reported in the journal Spine their results from an important study conducted on 52 patients with chronic whiplash pain. The researchers gave the patients either an anesthetic nerve block or a placebo to see if the cervical facet joints were actually involved in the chronic pain. They concluded that of these patients, the prevalence of cervical zygapophyseal joint pain was 60%. They found that the most common places for the facets to be injured were the same places where the spine undergoes abnormal stress, C2, C3, and C5, C6. In 1996, research from Japan was published that added weight to this line of study. These scientists examined the pattern of referred pain from the cervical facet joints by injecting each joint and mapping the pattern of pain that was reported. They created this distribution of pain from the various facet joints. As we can see, the facet joints refer pain in very similar patterns to what is seen in whiplash patients. In 1997, the Australian researchers published some of the most dramatic evidence that whiplash pain is related to injury to the cervical facet joints. In this study, Wallace et al. Decided to study the effectiveness of radiofrequency neurotomy, a surgical procedure that literally cooks the nerves that innervate the facet joints. 17 patients with long-term chronic whiplash pain were randomly given either the real surgical treatment or a sham treatment. 9 patients received the real treatment and 8 received the placebo treatment. The patients were then evaluated 3 months later. Wallace et al. Found that 67% of the patients who received the actual treatment reported complete pain relief. Only 38% of the patients who received the placebo treatment reported complete pain relief. Clearly, the real treatment seemed to relieve the symptoms at a much greater rate than the placebo. But the most remarkable finding was this. In every single one of the patients who reported complete pain relief from the real treatment, there was also a complete and immediate disappearance of the psychological symptoms that these patients had been reporting. The authors of this study wrote, "Somatization, obsessive-compulsive behavior, and depression can readily be seen as rational psychological responses to persisting pain that medical practitioners have not been able to diagnose and treat, and which has been attributed to malingering. These rational responses should disappear if the underlying pain is successfully treated. This is what occurred in the present study." So not only did this study show that the facet joints play a strong role in the issue of chronic whiplash pain, but it also demonstrated that the psychological distress that so often accompanies whiplash is a result of chronic pain, not the other way around. When we look at all the engineering and medical literature that has studied the issue of facet mechanics and symptoms, we see that there is strong evidence that facet joint injury causes pain after rear-end collisions. Some new research, however, shows that there may be other injury mechanisms from low-speed crashes. Some recent studies have focused on the issues of muscle injury and spinal nerve damage. Muscle pain is an extremely common symptom after rear-end collisions, especially in the acute phase of the injury. In 1995, a study by McConnell reported that tenderness of the anterior neck muscles was one of the most common symptoms reported by their crash test volunteers. In fact, high-speed footage of these same tests showed that the test subject's neck muscles bulged visibly during the early phases of the crash. New research by Sigmund shows that the muscles in the neck may tighten during the early part of the collision as the head begins to extend backwards. Not only may this result in a strain of the neck muscles, but it also seems to increase dramatically the amount of compression that the cervical spine experiences. As we saw earlier, this compression plays a huge role in the mechanism of injury from low-speed crashes. In short, this neck muscle reflex that is designed to protect the body actually may result in greater risk of injury. In 1986, Aldman wrote that rapid extension and flexion, like that seen in low-speed rear-end collisions, might result in rapid pressure changes in the spinal canal. This was studied by Onkren in 1996, who subjected pigs to whiplash trauma. The study discovered that there were dramatic pressure changes in the spinal canal just as Aldman had predicted. These results were duplicated by Swedish researchers in 1999. Obviously, it is impossible to measure spinal canal pressure changes in living human occupants, but a team of Austrian scientists conducted the same type of study with human cadavers by subjecting the specimens to whiplash motion. They found that the human spine also showed dramatic pressure changes during whiplash motions, and that this pressure pulse occurred at the same time that the rapid S-shaped curve is forming in the spine. The question is, can this rapid change in pressure cause injury? Svensson et al. Was able to study this to some degree by examining the nerve tissue from the swine they used in their study. They found that while the cervical vertebral joints themselves showed no signs of injury, the ganglion of the spinal nerves shown here displayed evidence of nerve cell membrane damage. These indications of damage were most prominent in the area of C6, C8. As we saw earlier, this is the same area of the spine that is subjected to abnormal rotation. The authors of this study hypothesized that the rapid pressure changes in the spinal canal can create a great deal of strain on the spinal nerve roots, which in turn could result in pain symptoms after a low-speed crash. There are literally dozens of factors that can increase the risk of injury from a low-speed car crash. A few of these include head restraint positioning, occupant gender, occupant position, and occupant awareness of the impact. Head restraints are probably the easiest way to prevent injuries from rear-end car crashes. Unfortunately, many people are injured each year because of an inadequate or improperly adjusted head restraint. In 1997, the Insurance Institute for Highway Safety studied 200 different new vehicles and reported that only 3% were found to merit a good rating. More than half of the head restraints in these new cars were graded poor at protecting occupants from injury in rear-end collision. Poor design is just one part of the problem. The second part is that most people think of head restraints as head rests and adjust them too low. A 1996 study by some British researchers recorded the head restraint position of 1,900 vehicles at an intersection. They found that only 25% of these vehicles had the head restraints adjusted in the up position. A properly designed and adjusted head restraint can make a big difference in the risk of injury during a low-speed crash. Here we see an animation of a collision with no restraint. and one with a proper restraint. A good head restraint protects the cervical spine by reducing the amount of differential movement between the torso and the head, and can eliminate the S-shaped curve that can cause injury to the spine. The key to proper head restraint adjustment is to increase its height and reduce the horizontal distance between the head and the restraint. According to insurance industry guidelines, a good head restraint is positioned no lower than a few inches from the top of the head and no more than a few inches behind the head. A study conducted by the insurance industry examined the role of head restraint position in a large number of people injured in rear-end collisions. They found that 29% of women drivers reported neck symptoms with a head restraint 0 centimeters below the head's center of gravity. But 69% reported symptoms when the restraint was more than 6 centimeters below the head's center of gravity. So, a properly adjusted head restraint can dramatically reduce the chance of injury in these crashes. Another factor that increases the risk of injury is gender. Consistently over the last 40 years, research shows that women are much more likely to be injured in a rear-end collision than are men. Various explanations for this phenomena have been put forward, but the latest studies seem to show that it's the smaller size of the female neck that increases the chance of injury. A Dutch study from 1998 reported that a 20% reduction in neck circumference resulted in peak head accelerations nearly 2.5 times larger. Occupant position is yet another factor that can increase or decrease the risk of injury. Engineers who conduct low-speed crash tests with human volunteers make sure that each occupant is facing straight forward, sitting upright, and has a proper head restraint. They do this to remove any possibility of injury in the volunteers. In the real world, an occupant who is tall may be injured because the head restraint is too low to protect him or her. Or, the occupant may be leaning forward, which can dramatically alter the amount of acceleration that the torso experiences in a crash. And probably the most dangerous position for an occupant to be in during a crash is with the head turned to the side. Why? Because the human head and neck cannot simultaneously rotate and extend. You can try this for yourself. First, bend your neck backwards. Next, turn your head to the side and then try to bend your neck backwards. It is very difficult. Now imagine your head turned to the side while being struck from behind. We turn our heads routinely while driving, whether from talking to a passenger in the car, or from looking around while stopped at a red light, or from turning in reflex upon hearing skidding tires just as we're about to be rear-ended. The bottom line is that most occupants are not sitting in their car seats in a way that will prevent injury during a crash. Asking whiplash patients about their position at the time of the impact is important, as it may help explain some of the patient's symptoms. The final risk factor that we will look at is occupant awareness. The medical literature on whiplash is fairly clear that occupants who are aware that they are about to be hit and have a chance to brace themselves are less likely to be injured than those who are unaware. An occupant who braces for the impact has a better chance of preventing the abnormal motions that cause injury to the spine. One of the most difficult problems in whiplash is the issue of no vehicle damage. Many people find it impossible to believe that a person can be injured in a collision in which the car was not visibly damaged. The engineering literature on this issue, however, is quite clear. There is absolutely no relationship between the amount of damage to the car and the chance of injury. In fact, a study by State Farm Insurance substantiates this lack of a relationship. This study found that of all the women they had studied who had whiplash symptoms, half had been injured in a car with less than $1,000 of vehicle damage. The first thing to realize is that an assessment of no vehicle damage may not even be accurate. Here is a photograph provided by Future Forensics of Bellevue, Washington. It shows the front of a minivan that was the bullet vehicle in a low-speed rear-end collision. The insurance company in this case said that there was no vehicle damage to this van, and that there was no way that the occupant of the target vehicle could have been injured. Upon closer inspection, however, it is clear that this accident was hardly minor. Here we see a photo from underneath the bumper showing damage to the unibody of the vehicle. Furthermore, analysis found that this undamaged vehicle needed 6.5 hours of work to straighten the frame, with a total estimated cost of repair of $1,300. This is a photograph of a car that was struck from behind and has already been repaired by the insurance company. The repair consisted of replacing the bumper cover and was considered to be a minor collision with very little property damage. Again, closer examination shows this is far from the truth. Removal of bumper covers shows that the bumper reinforcement has been broken from the impact. Removal of the bumper reinforcement shows even more damage, as we can see here. This rear portion of the car should be straight, and has been pushed inwards by the force of the impact. Again, this was a car that was considered to have no significant vehicle damage. Closer inspection revealed that in reality there was damage, and that it took a significant impact to cause such structural damage. As we can see from these photos, the only way to actually determine whether or not a car has no vehicle damage is to take it apart. Another misconception is that bumpers protect people from injury. The truth is that bumpers are designed to protect the car from damage, not the occupant. Furthermore, just because a bumper rated at 2.5 miles per hour is undamaged, it does not mean that the collision was less than 2.5 miles per hour. This is from a press release from the Insurance Institute for Highway Safety. Car bumpers are required by federal regulations to resist damage to the vehicle's bodies in collisions at 2.5 miles per hour. Most car bumper systems include foam or other means to absorb low-speed crash energy with little or no damage, and these bumpers often protect cars in impacts at higher speeds than specified in the minimum federal requirements. Furthermore, it is a mistake to assume that all cars are built the same. Here is a clear example of how the construction of a car can dramatically alter the amount of damage it suffers in a low-speed crash. In 1997, the Insurance Institute for Highway Safety tested the bumpers of 6 luxury automobiles. The 1997 Mercedes E420 ended up with $1,066 of damage after backing into a stationary barrier at 5 miles per hour. On the other hand, a study by Sigmund et al. Subjected a 1990 Honda Accord to over 100 crashes of up to 5 miles per hour, resulting in just minor bumper scuffing. While the car suffered no damage, the occupant accelerations measured during the crash test ranged as high as 12 Gs in the 5 mile per hour collisions. So clearly the amount of vehicle damage, visible or not, has no relationship to occupant accelerations or the risk of injury. As a matter of fact, a vehicle with no damage may actually experience higher G-forces than one with extensive damage. Robbins wrote that a stiffer vehicle will bounce in response to a crash rather than absorb the energy of an impact. This chart by Robbins shows that the less a vehicle is crushed during a rear-end collision, the higher the acceleration the car experiences. The concept is acknowledged by the Insurance Institute for Highway Safety when they wrote, "Vehicles with stiff rear-end structures and/or seatbacks produce greater torso accelerations, making it harder to keep a motorist's head and torso moving together. This means whiplash injury is more likely to occur." The final issue that we will address is the common trend by defense accident reconstructionists to calculate an occupant G-force from a collision after the fact. Usually these calculations show that the force of a collision was extremely low, and they often claim that it is impossible for an occupant to be injured from the crash. There are many errors in these types of reports, and we will now look at how it is virtually impossible to accurately assess the amount of acceleration this way. First, it is possible to calculate the acceleration that the target vehicle experiences, but you need to have some very important pieces of information before you can do so. This formula here is simply a different way of writing the conservation of momentum formula we saw earlier. We can calculate the final velocity of the target vehicle, or V2, if we know the mass of the bullet and the target vehicles, the striking velocity of the bullet vehicle, or V1, and the coefficient of restitution of the collision. The coefficient of restitution simply measures the elasticity of the collision, or how much bounce the cars have when they collide. So the accident reconstructionist is immediately in trouble. First, there's absolutely no way for him to know what the striking velocity was just by looking at the exterior of the car. A skilled engineer could examine the damage to the cars and provide a rough estimate of the closing speed, but it would be an estimate of a range of possible speeds and not a definitive speed. The coefficient of restitution also causes problems for the accident reconstructionist, because the only way to determine this number is to take identical cars, crash them together under careful examination, and measure the amount of elasticity. This is obviously hard to do and would be very expensive. The bottom line is that we cannot calculate an accurate estimate of the delta V of the target vehicle without these important pieces of information. We might be able to estimate a range of possible delta V's upon closer analysis by an engineer, but this would just be a range of values. Despite the fact that you cannot accurately calculate delta V after a crash, many accident reconstructionists go even further and provide a calculation of peak occupant acceleration. Let's examine how ridiculous this is. This graph compares the data from 9 different engineering studies that have measured peak occupant accelerations in low-speed crash tests. As we can see, the peak accelerations vary widely, even in crashes of the same speed. The reason for this is that there are literally dozens of different variables that determine how the occupant is accelerated during a low-speed crash, and any attempt to calculate that is impossible. As we've seen in this video, there have been some important new discoveries that can help us understand how people can be injured in low-speed crashes. New discoveries should help us not only understand how to treat patients who have been injured in rear-end collisions, but also reduce the number of such injuries in the future.